clinic that I was working, like, helping out with some nursing students one day, and they were, their teacher was talking to me, and they're like,
Good
yeah,
day.
it's so important, like, actually,
You know, I agree.
Spanish your whole life.
Darn cold outside.
Close.
That is fair.
Not quite.
I definitely don't like that it's been so
This
inconsistent.
is not-
Like, I'm a southern boy, and I feel like I need to curse some lows.
Okay.
Or, what is it, mittens? Is that what they use?
What?
Oh, no, it's just these.
You look like a penguin.
Quack.
That's now. Yep. The reason you weren't a biologist.
You were right. Last bio class I ever had was high school.
You didn't have to take any bio classes or anything in college?
No, because I passed AP bio and history today. Also, I don't think the physics major here needs any bio courses.
But the bio needs physics, that doesn't make sense.
Well, that's because on the list of scientific objectivism, you got math on this side, then physics, then chemistry, then biology. Bio is applied chem is applied physics, and physics is applied math. So you kind of need everything in that direction.
And Professor Alfar, I was tutoring this young lady in general chemistry too yesterday. And I was looking at it, I was like, man, this is all physics. And I recall when I realized that last semester, and made me drop my chemistry major. I was very upset about it.
Oh, no.
I realized all the chemistry stuff that I like was just physics stuff and just physics.
Yeah.
See, I've gotten far enough that I still can live in denial that that fact is true.
I realized it very quickly in organic chemistry, and I did not like the chemistry part of chemistry.
Oof.
That's unfortunate.
Yeah, in retrospect, it was the more physics part that I enjoyed, more so than memorizing what reacted with what and dripping things slowly and other things
Sometimes you get to dump it very quickly.
very quickly.
Yeah. And then you spill it, and then it's corrosive, and then you have a mess, and then the professor freaks out.
And then they have to use the decontamination shower for the first time in a decade.
And upstairs in my lab, there's a bunch of vials of non-dissolved chromium. That's a carcinogen. Good stuff. It looks like
Yeah.
glitter.
Everything's
The alkali metal samples floating in oil.
To each their own, man.
Well, I want to know if there's explosives in the building. I need to be aware.
Not yet. Wait, I'm sorry, that's not like, right. Wait, yeah, they can help you with that.
Are they teaching you the recipe of thermite? I'm pretty sure that's illegal.
I don't think so. We don't use any of that in our lab. That doesn't mean that we don't have it. There are chemicals upstairs from before my mom was a student here, so,
Oops.
yeah.
You renovated the building and didn't renovate the supply closets.
They did not renovate the building.
Well, speaking of chemistry, some of today's material is actually probably stuff you've seen directly in chemistry, at least some of it. Because we've been talking about the expansion of solids, a little bit the expansion of liquids, before we end what is arbitrarily labeled as Chapter 10. We're going to talk a little bit about the expansion of gases. Call back to that little gem over there on the board.
Perfner.
Additionally, just some notes. For one, the first homework and quiz have been moved to their correct due date of next Tuesday at midnight. So we have all this week and this weekend to work on those. On Tuesday, we can come in, we can ask all of our questions, and then it'll be due that night at midnight after class. That is how I intend on it working the entire semester. If for some reason there's a hiccup and the machine decides not to do that, please tell me and I'll fix it promptly. I'm also going ahead and put up the Chapter 11 assignments. Not that we've started Chapter 11, but they're there so that you can begin them when we do. And usually you want to try to get things up sooner than you need them instead of after the fact. So those are there. I definitely recommend beginning to look at the 11 homework at least, because there's a decent chance we'll probably get into the beginnings of Chapter 11 today. Get those notes pulled up. So today we're going to be probably finishing up chapter 10, just not the homework to do in about a week. And we also, reminder, have lab this week. So between Tuesday, Wednesday, Thursday, just make sure you come to your assigned section. Each individual section doesn't have that many people in it, so there's a chance you'll look around the room, see a person, and that's your lab partner. But because each section is so small, it doesn't really matter which one you attend if for some reason you need to hop into another one for a week. Or if you know which ones the people you'd rather work with are in, you can work out amongst yourselves which one you'd rather come to. The Tuesday one is currently the largest section, just to keep that in your heads. I've got about 3 different setups in 126, which should be enough for everyone to have a small team working with the tools on opposite ends of the table. And then I'll wipe everything down before and after. And all lab times are slated to last 3 hours. I don't expect anyone to take 3 hours most of the time. Most labs can usually be done in about 1 or 2. That said, if one does take you longer than normal, it's fine. You're okay. And I don't recommend rushing either, but just to remind, what was the point I was trying to make?
It shouldn't take us very long.
Right. But if it does, don't panic, because I'll be there helping the entire time. Quick question. Has anyone in here not used the new kind of tablet data collection tool that we have in the department now? Okay.
What?
It's literally like a Samsung tablet that a specific company literally reprogrammed. It's okay though. Every single lab, I'm going to give the introductory lecture and talk about the equipment, and that'll include a lesson or a refresher on how that thing works. I've already talked a lot of specific detailed information. How are you guys doing today?
Alive and well.
Good. Let's keep it that way. Any questions, comments, concerns, needs, or haikus before we take it?
Do you walk to work in just that jacket?
It depends on the temperature.
It was 28
Yes.
degrees this morning.
Hmm?
It was 28 degrees this morning, sir.
It was, but I didn't actually walk today because I woke up in Irma this morning. So I drove straight from there.
It's just the way that you phrase that. I woke up in Irma. Like, it wasn't intentional. You just happened to be.
I have real bad sleepwalking.
You know?
Even all the way there, well, that's pretty impressive.
I mean, who has time for cardio when you're awake? Might as well offload it to your sleeping hours. The issue is if you wander away. It'd be nice if I could just go in circles around the apartment.
Just put a weight on one ankle and
Yes,
you'll be good.
capitalize on centrifugal force. And then I'd get lopsided.
Well, you can alternate each night which ankle has the weight.
You know what? That's good. Pat that. Anything else?
How far do you live from here?
I currently have an apartment in town. It's a 20-minute walk. But my fiance is in Irmo, and I spent last night over there because it was our anniversary.
Aw, happy anniversary.
Thank you.
I know it's supposed to remind me of it.
Yeah, I'm from Columbia, so I lost my train of thought again. So I'm familiar with it.
Just outside of Columbia.
Okay, cool. Like the last member of my family that actually lives there, or around here. Anything else?
I guess we can learn physics now.
I mean, we gotta learn something. The tests are gonna happen, whether you want them to or not. So, like I said, everything expands when you heat it up. Solids, you heat it up and expand, that's kind of the end of the story. Liquids, you heat them up and expand. And liquids are kind of weird. They're just a little funky in that they don't have a definite shape, but they do have a definite volume. So, by and large, the temperature is the only thing affecting its volume at any given moment. Gases are the weird ones, because gases have no definite shape and no definite volume. You can force a gas into about any volume you want, as long as you make sure that the variables are right. So, while we're on thermal expansion, we're going to refer back briefly to the kinetic theory of gases to look at the expansion of gases as opposed to liquids and solids. Now, everything, when you heat it up, its particles will become more excited, they'll be moving around more, they're bouncing off of each other. That means they're also going to bounce off against their container more. Now, solids, container isn't super important for a solid because it'll maintain its shape even if it's not in a bowl. Liquids, the container does matter there, but because the liquid's not going to be changing volume anytime soon, we don't really bother doing this math for liquids very much. But for gases, the volume of a gas depends on, or the volume of the container holding the gas depends on several key things, including temperature, pressure, and the amount of gas present. And so all three of those variables have to be taken into account when examining the present volume of a gas, but also the expansion of a gas. So instead of our normal formulas that we've been looking at for linear and volumetric expansion, we instead refer to our old friend here for the expansion of gases. This one formula takes into account the pressure acting on the gas, the amount of gas present, and the temperature of the gas, all into determining what its current volume is. And this is the kinetic theory of gases. I believe, though, the formula is the ideal gas law. So called because in order to use it correctly, we do have to make a couple assumptions about what an ideal gas is. Worth writing them down, worth remembering them. So, Phys1510 is named ideal gas law. Who hasn't seen this before?
Go back really fast.
Well, if I ever go too fast and you want to keep copying, please let me know.
For the second one, the collisions are fully elastic, which means that there's no like repulsion in.
Sorry, say that last part again.
The collisions are elastic, which means that there's no like repulsion and attraction. Can we assume that here too, or no?
We do assume that the collisions between the molecules are completely elastic, which is just to say that all of the thermal kinetic energy present in the collision remains as thermal kinetic energy, and none of it gets wasted in the environment somehow. But it's already thermal energy, and that's the form things get wasted in the environment in, so you can't really lose it anyway. But yes, we assume they are elastic because when a molecule hits a molecule, it's just going to bounce off, and they can't really deform. They can't really crunch and get smaller like a car bumper can. So we assume that all the energy stays in the system. That they are elastic collisions both with the molecules, but also with the edge of their container.
Yes, sorry, that's great.
Okay. Moving on the slide. Okay. Next slide is just looking back at the ideal gas law formula. And I'm going to briefly. This one formula contains everything that relates to the volume of a gas and all the things that affect that. P is pressure, which could be measured in two different things. It's one of the frustrating cases where there are two metric units that are still both in circulation, although there's actually even more than just two. We got pascals and atmospheres. Atmospheres is based on the amount of air pressure you are feeling at the moment. You are currently under about 1 atmosphere worth of air pressure because there is 1 Earth atmosphere of air above you. Pascals, I actually don't know what the base unit for a pascal is. I just know the conversion. 1 atmosphere is 101,325 pascals. So the pressure is going to affect the volume of a gas. This is both the pressure that the environment exerts into the gas itself, but also the pressure that the gas exerts outwards on its container. Pretty much every experiment, we're going to assume that the gases in question are contained in something, because it's very hard to measure the volume of gas that isn't contained. So let's say we have our container, poorly drawn balloon, filled with lots of poorly drawn air molecules. If this balloon exists at sea level, there's going to be a bunch of air pressure pushing into the balloon on the sides. Meanwhile, the gas inside of the balloon, those particles are colliding with each other, but also the wall of the balloon. They are going to push out in all directions. And Newton's third law tells us for every action force, there is an equal and opposite reaction force. So typically, the pressure in and the pressure out will be balanced. A balloon at standard atmospheric pressure, the gas inside will be exerting standard atmospheric pressure against the pressure outside the balloon. Things do tend to get weird if the two pressures aren't balanced, though. This can get particularly nasty on humans, but it can get kind of funny on things that aren't humans. Yes.
So, is R different when we're using atmosphere?
Yes. The gas constant R does depend on what other units you're using around it, and I didn't address that yet. If you are using atmospheres instead of pascals, it's 0.0821 instead of 8.31. This is an experiment that I hope I can physically build with supplies around the school at some point, but I hope you've seen something like this before. Marshmallows are basically just sugar balloons, in that they're just air sugar. And so, if you put a marshmallow in a vacuum tube and you remove the air around it, there's less air pressure pushing into the marshmallow. So the air inside the marshmallow pushes out on the marshmallow itself. When you let the air back in, the air pressure pushing into the marshmallow increases and it... Well, but he's still happy. He's alive, he's just smaller. Same thing happens with balloons and plastic bottles. I'm trying to think of all the things I've put in vacuum jars before. I was once able to very selectively control the pressure inside the jar to make a red balloon beat like a heart. So, usually pressure in will equal pressure out. If one of those two sides is different from the other, something is going to change to account for that. If the pressure outside the balloon is less than the pressure inside the balloon, it will expand. If the pressure outside the balloon is more, it will shrink. Same kind of thing happens to humans. If you change the air pressure on your body, go up on a high mountain, pressure is less, your ears pop, come back down, pressure is more, your ears pop again. Go far under the sea level, there's more pressure pushing into you. That's going to compress the nitrogen in your blood. If you rise too quickly, then that nitrogen will expand too quickly and it gives you bends. Similarly, has anyone watched sci-fi to the point where you've heard that if a human is in the vacuum of space without a suit, they will explode? That's because of this. Since we have air pressure on our bodies have to exert an amount of pressure out to balance it out. So right now, literally your insides are pressing against you outwards to counteract air pressure. And I think this is based on your blood flow. So if you go into space, like all of a sudden there's no air around you anymore, your body's still going to push out even though there's no air pushing in anymore. And you will literally...
So if you went to like Jupiter, would you implode?
You would implode for lots of reasons on Jupiter, assuming you weren't torn apart by the giant storm that is its entire atmosphere.
I ain't nothing. I'm good with that.
We don't know what the surface of Jupiter is because every probe we've ever sent was destroyed by the howling winds that is its stormy atmosphere.
Built different.
Built different, just built the whole thing into solid platinum.
Jeremiah Jackson's making his way to Jupiter next week, actually.
Who is?
That's me.
Oh, hello,
That
sorry.
one.
I'm still learning names and I feel bad.
Don't worry, you'll read up about me later.
I look forward to it, actually. If I get the scientific article on my desk, can I get you to autograph it?
We'll see.
I appreciate your consideration. So, pressure affects the volume of most things, actually. That's the wrong house. Next, N, number of moles present. Has anyone never used moles before? Okay, very good. Just a measure of how much physical stuff is there. The more stuff present, the larger its volume is naturally going to be. R is the gas constant. Which version of it you use depends on what variables you use in other parts of the formula. The 8.31 in the notes assumes you are using pascals. Pascals and liters, I believe. This one assumes you are using atmospheres and liters. I might be assuming pascals and meters cubed, actually. I think so. Yeah, the 8.31 is pascals and meters cubed. Let me write that down. So we have two different gas law constants depending on the various variables you could be plugging in. Last is temperature. Hotter something gets, the bigger it's going to get. Because this formula doesn't have a delta T in it, you have to use kelvins. No other unit will apply here. And Avogadro's number, just handy to have on hand. Like be on formula sheets and such, but if you want to copy it into your notebook, that is good. This is, I assume, is just entirely a review for you guys. Just reviewing it here, where it fits in with the thermal expanded. Questions?
One time I got told if there was a mole of evidence, it would cover the United States a mile high.
Well, Yeah. That's a lot of M&Ms. I don't know the volume of a single M&M off the top of my head, but Mile High for the entire US? That's many.
Maybe I missed what I was told in high school. It's been a while since I was there.
We do have the entire history of humanity in our cell phones these days. You piqued my interest, so I want to know before we move on. My calculations show that the mass of 1 mole of M&Ms is 5.23 times 10 to the 23rd grams. Meanwhile, the Earth has a mass of 5.97 times 10 to the 27th grams. So, 1 mole of M&Ms is 1,000th, 1/10,000th of the entire Earth. Which means that's probably more M&Ms than ever existed ever.
I just need the means to produce that many.
I
How
like
deep
chocolate,
would a
but
bowl
I don't
of
think I
M&Ms
need
be?
that many.
Well, it's
You
not
could
just
make a
me.
moon out of that.
I don't know.
Actually, if you had that many in a ball, it would probably form into a meteoroid with its own gravity.
Only one way to find
An
out.
M&M meteoroid. Why do I do this? Moving on. Okay. We have a formula. Should probably use the formula. So, quick review. We have an amount of gas at a temperature, at a volume. Let us find what the pressure it is under. Let us find the pressure it is under.
Oh, just kidding. This says it would be 52 miles deep. This is according to the ACS website.
Well, assuming that such a mass would be 1/10,000th of the entire Earth, and chocolate is not that dense, I believe you. I believe that could happen.
I had calculations for that.
52 miles deep. Nothing would survive. The Hershey's company has gone too far. What's 25 degrees Celsius in kelvins?
298.
Very good. That's a very common number. Keep it somewhere easily accessible in your frontal lobe. Do you remember things in your frontal lobe?
What?
I'm asking hypothetically a biology question, I think. What part of the brain do you remember things with?
I don't remember. That's gonna be like your upper brain now. The cerebral cortex. Something like that. Just help my sister out here.
They're assuming they can have it.
Like the hippocampus or something? I don't know.
Sounds right. I had
Oh,
so many
yeah,
long
because
times
you
since I had to
remember if
learn.
you saw people on campus. Yep.
Yes, Miss Fry's,
Is
yeah.
that actually the trick?
I'm
Yes,
sorry.
it is.
Wait,
It's-
say it again.
She was like, hippocampus is like your memory of like processes and like where you go. And she was like, if you think about it, like if you saw a hippo on, like something about like how would you get around campus or like how would you show a hippo on campus, something like that.
Gosh,
But
that
it
was
helps you
good.
remember it.
I mean, I'm not going to forget it now.
Could you imagine a hippo walking around this campus with that? That'd be a danger.
I
I
bet
mean,
the
they
geese
try to
would be.
live in the duck pond.
And somebody's gotta go get those things.
Hippos are more dangerous carnivores than sharks or most carnivores, actually.
They're actually not carnivores, but they're the most dangerous animal.
In terms of human deaths,
Yeah,
yeah, I've heard that.
but they are herbivores. They just kill people.
Oh, no.
Because the people get their space.
It woke up
They're
today and
just
chose
what they
violence.
tell people.
I would have assumed they were omnivores. Oh. Okay, the most dangerous omnivore, that's not a title I was expecting to hear today. Is that a joke question?
Where did you, is your place on too?
Oh. I'm not entirely sure.
He was thinking about the imminent.
I read, maybe, I read that 5 and my brain did something strange to it, I apologize. I have this quirk, I don't know if it's a named condition or not. There's a number in my head, I'll read the clock, I'll know what time it is, but if I go to write down the time or say it out loud, one of the numbers gets transposed. And I'll know what it's supposed to be, it's just what comes out that is wrong. Okay, we know N, we know T, we know V, we want P. You're pretty set to plug things in. What value for R do you think we should use this time?
The 0.082, 1.
Very good. I would concur, because our volume's in liters, and I want the answers in atmospheres anyway, because I find that easier for me to conceptually understand. I like atmospheres for that reason. So, P times 1.5 equals 0.75, 0.031. No, 2.1. And that gives us 12 and some change, if I remember correctly.
That's right.
What's the change?
0.2.
2.3?
Yeah.
Didn't remember. That's weird for me.
Usually the hippocampus, I see.
Ah, yes. The hippo told me a number. All right, that's actually a lot of pressure because it's literally 12 and some change times what you're experiencing right now. So I wouldn't recommend replicating this procedure. And to adjust it just a tiny bit, we are going to increase the temperature and reduce the volume. Before even doing much math, you can go ahead and keep writing and solving, but without even doing math, just looking at what is physically being done, do you think pressure is going to go up or down? Up. Why?
Because it's smaller space and they're moving more.
Right. Smaller space, they're naturally going to push against their container more. Higher temperature means the particles are bouncing around more, which means they're going to press up against their container harder. We can plug the new numbers into the same formula to get our new second number. So we're going to relabel this P1, down P2 in a minute. But there also exists a variant formula you can use for changes in a system. This particular version assumes that moles remain constant the entire time, which is generally how most scientists will perform their experiments. They want number of moles to stay fixed because that's the single hardest thing to control and that's the single hardest thing to measure. And final pressure, I think it's 15 change, no, 14.
You're right, for some,
15 and what is it?
I have 0.17.
20, sorry, one more time.
0.17. I could be wrong though. I don't remember correctly all the time.
Did you guys get 14? Yeah, 14.9, 14.19.
I remembered it as a 14. Okay. Temperature went up, so that's going to be 303 instead. Volume dropped, so that's going to be 1.25 instead.
I am now getting the 13.9 number.
Okay. There we go. Well, that rounds up to 15, so. So, in general, volume goes down, pressure goes up, temperature goes up, pressure goes up. Any questions about this chemistry review? Yes.
How does like all the pressure in the universe or the atmosphere, how does that not outweigh what's inside of us?
So the atmospheric pressure on you right now is calculated based on the density of the air around you and how much air is directly above you. So 1 ATM of pressure is the entire atmosphere's worth of air on your head. The math gets a little tricky because the density does change on the way up, but we just set 1 ATM to whatever the barometer measures here and now. The body, humans were built to live on Earth's surface. So we were naturally calibrated to that number. I assume that's just how our blood flow just matches that pretty successfully, I think. This is edging a little more into biology than I can speak to super well, but from my own experience being a human on the surface, I know that we are at least able to exert 1 atmosphere out of ourselves. Air is not super dense. At least Earth's air isn't. 1 ATM, like cosmically speaking, isn't really a lot. So we're just well built.
Build this.
The more you look into like physics and other planets, the more you realize that we really were built for literally this planet. Because I've been reading about like the proposed Mars colonies, and that's just a terrible idea. You don't even need to watch The Martian to know that's a terrible idea.
They'll do anything to save the planet.
Well, yeah, there's no profit in it. Mars is a hot new thing. Make way more money.
Well, Tesla stock is spiking, dude.
Those GameStops for some reason. Okay. One last thing that is technically still part of Chapter 10. We're going back to that first formula that I showed you when we didn't really do much with. Now that we've talked more about the energy and the gases in general. So, thermal energy makes the subatomic particles move around, and they're going to move around at a certain speed based on their temperature. So we're directly relating temperature to kinetic energy now. This is a new, well, I showed you this formula before, but these were derived specifically to compare thermal energy to the velocity of particles. Kb is a constant, Boltzmann's constant, which is curious because this formula is edging more into the territory of Heisenberg. But because of this relationship, we can figure out how fast the particles in something are moving, mostly with gases, which are moving the most. To do so, though, you do have to know the mass of a particle and its temperature, which is generally pretty hard, but there's a couple of cases where we've managed to figure out. So, to end Chapter 10, using the same formula, there are 3 subatomic particles that make up all atoms: protons, neutrons, electrons. Neutrons you'll never find by themselves, because they always live in the nucleus. Electrons can be found on their own, usually in lightning. Protons are the ones that most commonly exist by themselves. You can't have a single proton, and technically that is an isotope of hydrogen. So protons are their own element, which is kind of cool. Which does mean you can set them on fire. Now,
That's all I need.
excuse me. So, we have a rough approximation for the mass of a single proton. And because there is hydrogen gas in the atmosphere, that does mean there might be some loose protons in the atmosphere in the form of H plus gas. So, assuming that this room is about 25 degrees Celsius, what would the speed of a proton be in this room?
Can you use Celsius in this?
You cannot. Celsius will only work if it is delta T. Good question, though. Always good to get clarity.
Would standard units be grams or kilograms?
Kilograms. In terms of physics, pretty much all of our formulas are regularly going to take kilograms unless otherwise specified.
So how are we to determine directionality of something like this? I see that little vector symbol over that B right there.
You know what? You are right. So technically, this velocity would have a direction. Every proton is moving in a direction. But A, in general, good luck knowing what direction any given molecule is moving in. B, because this formula has b squared in it, eventually you're going to get b squared equals blank. You're going to solve for b equals square root of something. That square root will inherently make the answer positive or negative something, which means even if you could know the direction of a specific molecule, this formula could never tell it to you, which is why I'm not going to ask. I'm just rechecking my work because we got a big answer. Anyone disagree with this math?
Mine's like, I didn't round anything.
That's fair. So at room temperature, gas molecules are floating. Pretty much every molecule is actually moving around very, very, very quickly in general, unless you're near absolute zero. The molecules inside your body, the speed won't be too much different of this because they're all the same temperature. roughly the same temperature as room temperature, if not warmer, because we're warm-blooded. Yes?
I understand that the units in meters per second, but how did we get that, units that we have?
Where did kilograms go?
The kilograms got, okay, so on this side of the equation, you've got kilograms times meters per second. Kilograms times meters squared divided by seconds squared. That is nearly, okay, that is the unit for joules. Kilograms times meters squared divided by seconds squared is a joule.
Okay.
Because this is just the kinetic energy formula. On this side, we've got joules over kelvins times kelvins. So the kilograms are absorbed into joules, and the temperature unit canceled out with the temperature unit of the Boltzmann's constant, and we fish the meters per second back out of joules.
That's something you not remember.
Sorry?
So that's something you not remember.
Well, I'm not going to let you forget it. Nope, we're going to be using that all year, actually. So, single protons move very fast. Other atoms are still going to have very high speeds, even ones that have noticeably higher amounts of protons and neutrons in them, because even an atom that has about 100 combined particles in it, its velocity will still be really fast. All particles at room temperature are booking in. The only reason you don't notice them is because they're constantly bouncing off of each other, and as a result, they don't really go anywhere. There's not single atoms ripping themselves out of your being because they're hitting other atoms and just going back where they came from. So we assume in ideal gases, and really ideal anything, that the net motion of all the particles is just going to cancel out. They are moving fast, but they aren't going anywhere. And after I fix a quick typo, that's chapter 10. At least everything that is arbitrarily labeled as chapter 10 in our textbook. Any questions?
Okay. Go through the joules thing again. 'Cause
Yes.
I got it so that it just cancels. So then how do you fish meters per second out of it?
Okay. Thanks, sir. So, this side, 1/2 mv squared, is the formula for kinetic energy.
Yes.
That means this whole side, before we do anything else, is a joule. This is 1 joule.
Yes.
So that means 1 joule is equal to kilograms times meters squared over seconds squared.
Yes.
Which means that the Boltzmann constant, since it's joules per Kelvin, is in units of kilograms times meters squared over Kelvin times seconds squared.
Yes.
Now on the right side, we multiply Boltzmann's constant by temperature in kelvins. That's going to cancel the Kelvin out and just leave us with the kinetic energy formula units again. Divide both sides by mass, kilogram falls away, and then we square root both sides to turn meters squared over seconds squared back into meters per second.
Okay. I'm drawing.
Units are cool. The units are cool.
They're useful because it helps to know where everything goes. I know there's been once or twice where looking at all the units and how they cancel out radically changed how I understood something. So sometimes it is worth the exercise of just studying the puzzle.
questions?
Okay. We've been going for one standard class length, and I haven't done our usual bathroom break yet. So, if you need a second to get some water, or the restroom, check your notifications, or otherwise just let your brain take a breather, now's a good time. In a second, we will at least begin chapter 11, so that we can resume with it next time.
Something that doesn't change volume is isochoric.
One more time.
Doesn't change volume, the system's isochoric.
See, I don't know of any word, but my brain is just trying to say isovolumetric. But that doesn't sound right. Well, no, isovolumetric is a word. Used specifically to refer to a type of contraction in the heart. There's also isovolumic. What is the word you were saying?
Isochoric?
Isochloric?
Choric. I-S-O-C-H-O-R-I-C.
Isochloric. Yes, that does mean constant volume. I didn't know that word, thank you. Yes, isochloric, isovolumetric, or isometric. I've been hearing the word isometric most of my career, and I had not looked it up yet. I feel really dumb now.
Stock was as low as $81 today.
Brad's got to get back on it. Keep Wall Street in check. Thank you for this article, Madison.
learned how to do that, and I can't remember how to do it, and it's been crazy.
Can you repeat that whole sentence, Diane?
Keep put in, just not.
Last semester, we learned how to find internal energy using translational, rotational, and vibrational energy of a
Yes.
molecule using degrees of freedom.
Okay.
Using just translational energy, and you have 1/2 RT per degree of freedom, then it's gonna be 3/2 RT equals your internal energy, which like is reminiscent of the equation you just gave us.
Yes,
So
so
I
I
was-
actually have in this next slideshow.
Really? That's a lot. Yes, and so we like had to figure it out for multiple molecules that had had vibrational and rotational energy. And I was trying to figure out how we derived those equations from the heat capacity of isoporic and isomeric systems.
I don't have that now.
I think I figured it out.
I believe in you. I just haven't had to think about that.
Sorry, it's not super relevant, I didn't mean to derail.
I mean, I encourage you to look into such things. I just haven't had that thought in a while, if ever.
I had to prove, like, we had to like prove it on our test.
Okay, then.
You and Dr. Gearhart should hang out sometime, you would go along.
He was my chem teacher here, actually. I had him for 2 semesters. I don't know if he remembers having me as a student, but he remembered me enough to come down to my office to visit as soon as I got hired.
What about Dr. G?
I kind of specifically waited to take my chem classes to when I got him. So he's the only chem teacher I actually know. Speaking of chem, does this look familiar? No, that's not how I normally write it.
I literally just did this yesterday.
So, especially a lot of these early chapters is going to be a lot of chem review, which I hope that you guys, if not enjoy, at least can use and relate to. So, we already talked about what thermal energy is, what happens when some things have it. We're now going to talk about what happens when it starts moving between objects. And this is this formula, one way or the other, is how we calculate what the change in temperature of an object will be when thermal energy enters it or leaves it. So, I prefer writing it like this, actually, now that I think about it. Q represents heat flow. And that is measured in joules. It is thermal energy. It's basically just change in thermal energy. There's a weird misnomer that even I have a hard time actually saying correctly. Heat, the definition of heat, at least as far as physics is concerned, is the flow of thermal energy. My brain wants to use the word heat to just be a synonym for thermal energy, but the official definition of heat is the flow of thermal energy. So when you touch something, you don't really detect temperature, because again, you don't have a thermometer at your fingertips. What you're sensing is heat flow. All you feel is thermal energy entering me, how hot, or thermal energy leaving me, how cold. So you feel heat, not temperature, not thermal energy. And as thermal energy flows into or out of something, its temperature is going to change based on its mass and what it is made of. Is there anyone in the room that has never seen this before? It is okay. It is okay if so, I'd rather you tell me. Okay. So, familiar with the concept of mass and material affecting the rate, how thermal energy affects something. Okay, very good. So, on this set of notes, and also included in pretty much anywhere, any assignment where you would need it, is this table of specific heat values. I'm pretty much exclusively going to draw from the joules per kilogram side, because calories and gram. I already said that all of our formulas are going to use kilograms. That's just the physics standard. So already this is more the chemistry tab. Sorry, this is just the one that we like on this floor. And it's got all the old staples: metals being low, water being freakishly high. Freakishly high, actually. Steam and ice are like half what water is.
So the higher the number, the more easily, or the less?
The higher the number, the higher the specific heat, the less prone something is to changing its temperature. The number itself represents how many joules are needed to increase 1 kilogram of that material's temperature by 1 degree. It's kind of in the unit, as it says up here, joules per kilogram per degree Celsius. So if you have 1 kilogram of water, you'll need 4,168 joules to make it 1 degree warmer, which is a lot in terms of having heat and putting it into the water and keeping it in the water. And so the bigger the number is on this table, the slower it is to heat up. But once it gets hot, it's probably going to stay there longer, because that also means it has to give off a lot of heat to then go back to being cold, which is one of the things that makes Earth habitable, since water is basically a giant heat sink, and since most of the planet is water, liquid water, thankfully, it's absorbing a lot of the energy from the sun so that everything else doesn't. And because it keeps that energy, that keeps the ocean at approximately the same temperature year-round, instead of freezing solid in the winter.
Good.
And since most life on this planet is water-based, it helps us not freeze in the winter, and the grass, usually.
Some sacrifices must be made.
Yes? Oh. Some orange farms, whenever there's a big freeze coming, they will literally douse all the orange trees with water, so that the water on the trees has its thermal energy removed, and it becomes an insulating layer of ice instead of the thermal energy of the orange being removed and turning into nasty moldy pulp. When I was young, I accidentally thought that, oh, well, we're going on vacation. I'm just going to put all of this produce in the freezer so that it keeps while we're gone. And then we got back and it thawed out, and it was not a good time. Because when you kill the water in a cell, everything dies.
And like when the water freezes into ice, it releases heat from the hydrogen bonds.
So freezing is technically an exothermic process, because the water has to get rid of heat to become ice. So I don't know about the whole sentence, but if the water in a cell freezes, it will put heat into the non-water parts of the cell, in addition to expanding and probably lysing it. Did I use that word right? Last thing before we break, we have a camping stove, we have an amount of water, you're able to increase its temperature in an amount of time. So, very first thing we're asked, how much thermal energy do we need to boil this water? So, we have an amount of water. One liter of water. And fun fact about water. That means we should have 1 kilogram of water. So, they told us volume, but we can pull out the mass that we need from that. And it starts at 40 Fahrenheit. It's going to end at boiling, which is,
So what is that 40?
Sorry?
That is not 40.
You said 40, but you wrote 70.
I did, oops. I did it, see, there's that thing again.
You wrote the right thing. so.
Which is good. Didn't make this, I didn't put the same number out wrong both times. Okay, so it starts at 70 Fahrenheit, it's going to end at 212 Fahrenheit. Gonna have to do something with those. Fortunately, boiling in Celsius is pretty easy. And we know that it's going to take 4 minutes and 7 seconds for this whole process to complete. Why does my hand open it? So, we know, first thing we're asked, how much thermal energy does water need to boil? We know, starting at final temperature, mass, and we know that it is water. So we go back and consult the table. I remember what the table said, actually. I'm surprised. So that is the specific heat of water. And we are good to go to find our heat flow. Now, this formula has a delta T in it, so Celsius is legal. We do need to convert 70 Fahrenheit into Celsius first, though.
21.1 degrees Celsius.
Thank you very much. Well, sorry. Final minus initial, that's 100 minus 21.1. And that will tell us thermal energy required. Concur. Okay. That, scientifically speaking, is a lot of energy. This water went up by about 80 degrees Celsius with that amount of energy. Considering that tin's specific heat is about 20 times smaller, it would increase by 400 degrees with the same amount of thermal energy, approximately. So again, water's very weird properties are very beneficial to life on this planet. Second part, this is actually a thermal power question. How many joules per second are being transferred? That's straightforward. You want to take your total joules divided by total time. How many seconds total is 4 minutes and 7 seconds going to be?
I was doing 4 seconds.
You. So, joules per second, 330, 2754 over 247. Gives us 1,333.15 joules per second. Does the unit joules per second sound familiar? Watts. Joules per second is watts. So this is basically a power rating for this particular burner. And because thermal energy is energy, you can also have thermal power as thermal energy is either used or transferred per unit time. So do keep that in mind. We'll close it there for today. We do have lab this week, so if you have lab today, I'm going to run over to the lab room in order to open the door. I'm going to need to run upstairs to print a few things for the lab itself. But I'll leave the door open if you have lab today. If you don't have lab today, then have a wonderful day, and I'll see you soon. If you do, I'll free you even sooner. All right?
I figured out what I was talking about earlier.
Okay?
Because you have to determine the degrees of freedom based off the shape of the molecule for each type of energy.
Oh, right.
And so like, you have to take into account like the carbon dioxide, that it's not just one. So it doesn't just